So excess pressure inside a liquid drop. First application. So good afternoon all of you. So today afternoon discussion we'll discuss about for a liquid drop, a spherical liquid drop. So there is a pressure excess inside a liquid drop compared to outside pressure. So what is the value of excess pressure? How to calculate that excess pressure inside a liquid drop compared to outside? So let us consider liquid drop spherical in shape. Consider a liquid drop spherical in shape first. So let us say this is the liquid drop. Now, so let us say outside pressure is P naught. P naught is outside pressure. Are you able to see the screen? Excess pressure inside a liquid drop. Yes or no? Please reply. And let yes. Let Pi be the inside pressure. Let Pi be the inside pressure. P naught be the outside pressure. That is atmospheric pressure P naught. Okay. This inside pressure greater than outside pressure, no doubt. The pressure difference delta P is equal to Pi minus P naught. K minus P naught. This delta P is called excess pressure. Because of this excess pressure only air bubbles will blow immediately or water droplets also changes its shape. Okay, all these different phenomena you can observe. So the direction of pressure on the surface, it will be like this in all the directions on the surface. Okay, like this. Now let R be the radius of this liquid drop. Capital R be the radius. The radius of drop in a spherical shape. Radius. Now, because of the excess this now we need to calculate this delta P excess pressure in terms of radius and surface tension. Let T be the surface tension. Capital T be the surface tension of liquid drop. Surface tension of liquid. Are you clear this? T be the surface tension. Now because of this pressure there is a small increase in a radius of this liquid drop. That increase you can take like symmetrically. Symmetrically like this there is a small increase. So the small increase let us say dr. dr is the small increase in radius of the liquid drop. Now initial surface area. Let S1 be the initial surface area. Okay, that S1 is equal to 4 pi r square. Then final surface area after increasing is initial surface area. Final surface area let us say S2 that is equal to 4 pi r plus dr whole square. R plus dr whole square. Then there is increase in surface area. Increase in surface area of liquid drop because of the excess pressure. ds is equal to S2 minus S1. S2 minus S1 that is equal to 4 pi r plus dr whole square minus 4 pi r square. Are you able to following? Increase in surface area in all sides. That means total because of the increase in dr in all the sides. 4 pi into r plus dr whole square minus 4 pi r square. Are you able to following? So 4 pi into r plus dr whole square, r square plus dr square plus 2r into dr minus 4 pi r square. Okay. So my dear students, please react, any one of you, whether you are following this page or not. I need to understand.
Yes, sir.
Right. So here 4 pi into r square plus 4 pi into dr square plus 4 pi into 2r into dr minus 4 pi r square. 4 pi r square, 4 pi r square will be cancelled, right? And the remaining will be ds, excess surface area, increase in surface area is 4 pi into dr square plus 8 pi r dr, 8 pi r dr. See, dr is very, very small, increase in radius. Then dr square will be, suppose dr is suppose 0.1, 0.1 centimeter, then dr square will become 0.01. So that means increase in, that means square of that one will become very small. This is initially small, then square of that one is very, very small. So that we can neglect this term. This term we can neglect. So then ds is approximately equal to 8 pi r dr. 8 pi r dr. So due to this increase in surface area, there is an increase in surface energy. Increase in surface energy. Already we discussed. Surface energy is directly proportional to increase in surface area. Okay. So the surface energy increase is equal to du is equal to what you can write? Remember the relation surface energy and surface area. Du is equal to T ds. T is the surface tension into ds. Okay. Du is equal to T ds. Therefore, du is equal to T into ds. ds already from equation 1 you can write. From equation 1 and 2 you can write du is equal to T into 8 pi r dr. Okay. So this is equation number 3. So from equation number 3, du is equal to T into 8 pi r dr. Okay. Right. But this is equal to work done by the increase in pressure, whatever internal pressure. Work done by internal force or internal pressure. Then work done by internal force. Work done by internal force. dW is equal to what you can write? F into dr. Force into displacement. What is this force value? Internal force Fi internal. Here Fi is equal to pressure P, internal pressure into surface area, P into S. So actually this internal force you can say excess force, you can take delta Fi, then delta F, delta Pa internal pressure, excess internal pressure, excess pressure. Okay, dW is equal to force into displacement. That Fi can take delta F, that means excess force, similarly excess pressure. So the delta F I can write delta P into S, delta P into S, not delta Pi, delta P into S. Delta F is equal to delta P into S. That means dW you can write as delta F into dr. Okay. The delta F is delta P excess pressure into dr. The delta P into dr value how much? Sorry, delta P into S. Pressure into surface area. Na? F means pressure into area. So that what is the area of surface area at that time initially? 4 pi r square. So this delta F is equal to delta P into 4 pi r square. Therefore, delta P into dW is equal to delta P into 4 pi r square dr. This is the work done by internal force, excess internal force. Equation number 4. I can say 3 and 4 equal. Whatever work done will be stored as surface energy, work done per unit area. Then you can write delta P into 4 pi r square dr is equal to T into 8 pi r dr. Okay, from equations 3 and 4. Right. Then dr cancel, r one time cancel. pi cancel. Okay, then 4 is 2 times cancel. So delta P into R is equal to 2T. So this delta P excess pressure is equal to 2T by R. This is the final relation. Delta P excess pressure is equal to 2T by R, where 2 is the constant, T is the surface tension, R is the radius of the liquid drop. Radius of the liquid drop. Okay. So therefore, we derived a relation. Equation number, let us say 5. This equation 5 shows that excess pressure inside a liquid drop. Inside a liquid drop. Actually, that excess pressure, what I said, internal pressure minus outside pressure, atmospheric pressure. So this I can write as delta P is equal to Pi minus P naught. Here Pi is the inside pressure. Pi is the inside pressure. P naught is the atmospheric pressure outside. P naught is outside pressure or atmospheric pressure. Because outside atmosphere on atmospheric pressure. Now this delta P I can write as like this also. Pi minus P naught is equal to 2T by R. Pi minus P naught is equal to 2T by R. That means from this you can calculate inside pressure also. Pi is equal to P naught plus 2T by R. P naught plus 2T by R. Are you clear this, all of you?
Yes, sir.
Right. So this is about for a liquid drop, the inside pressure or excess pressure in terms of its surface tension. Okay. Right. Now, in that we can take about case studies. Suppose in that applications, cases first, soap bubble. In the case of soap bubble, what about the excess pressure inside a soap bubble? Excess pressure inside a soap bubble. What is the difference between liquid drop and soap bubble? Liquid drop is fully filled with liquid. Okay, then free surface is only outside surface. Outer surface is the free surface. Now I can take a soap bubble. The soap bubble is inside also empty. Let us say there is a layer, inside layer and outside layer, like this. It has certain thickness, that's it. Inside also air will be there, outside also air will be there. That means soap bubble having two surfaces. Two surfaces. Are you clear this point? Outer surface, inner surface. O for outer surface, I for inner surface. Okay. Then in such a case, very simple, that excess pressure you can write delta P is equal to, instead of 2T by R, you can write 2 times of 2T by R. You can do the derivation also, you'll get the same. Directly I am taking shortcut. Because of two surfaces, we need to consider two surface area. So each case 2 times it will be multiplied. Finally, excess pressure also it will come 2 times. So that 2 into 2T by R. Are you clear this point? So the delta P will become 4T by R. Are you clear this? For soap bubble, excess pressure will become 4T by R. Understood all of you? Because of the two surfaces, inner surface and outer surface, you need to take the surface area 2 times, so that 2 into 2T by R. So everywhere the calculation 2 times will be continued, so that it will get 4T by R. Okay? So that is about soap bubble, excess pressure inside a soap bubble. Next, case 2 you can say Suppose there is a bubble, that means a liquid bubble or soap bubble, whatever, a bubble, air bubble inside a liquid. Air bubble inside a liquid, just inside a liquid. Let us say inside a water. You can imagine. So this is the layer of water. So within the layer of water, there is a bubble. You can imagine air bubble, you can imagine inside a water. Yes or no? This is the air bubble. Okay, let us say radius is R again for this also. Now, what is the excess pressure in a air bubble inside a water? Delta P. Either 2T by R or 4T by R. Anybody, any guess? How many surfaces does it have, first of all? Air bubble inside a water. Air bubble inside a water. How many surfaces does it have? 2. Munishwar. 2 surfaces is wrong. Munishwar
4.
Kumar. No, only one surface. See here, outer surface is connected with water. Outer surface is connected with water. Only inner surface connected with air. Okay. That means this inner surface only you have to consider. Because outer surface is connected with water means is liquid, containing liquid. Okay. That is the free surface. So that only inner surface is the free surface. Then only one surface. One surface means it is acting like a, again, liquid drop only. That means excess pressure you can take 2T by R only. That is the surface tension. Are you clear this point? For air bubble inside a water, again the excess pressure inside air bubble you can take delta P is equal to 2T by R. 2T by R. This is about the important application or case you can take. In the case excess pressure inside a air bubble which is placed inside a water. Okay. So this is about an important point. Now all these applications are. Now you can compare a soap bubble and liquid drop. Suppose third case, soap bubble and liquid drop. Or air bubble inside water. You can take anything. Now in which case excess pressure will be more? In which case excess pressure will be more? In the case of soap bubble, very clear, delta P is equal to 4T by R. And here delta P is equal to 2T by R. Okay. That means you can take like a soap bubble outside and soap bubble inside water, whatever. In that case, suppose surface tension will be same. Then inside the water only 2T by R. Outside is 4T by R. So that normally bubble having more excess pressure compared to liquid drop or a bubble inside the water. So that is the point you have to understand. Next case you can take. Suppose you have a pressure difference across a film. Suppose there is a film like this. You know already free surface on the container. This is the free surface of the liquid. So for this film, okay, this film is like a spherical in shape. That means you can imagine a large film like this, spherical in shape. In that case, the excess pressure difference across the film having one free surface. This is the only free surface, top surface. Then in that case, again excess pressure delta P is equal to P inside minus P naught, that is equal to 2T by R. That means whenever you can talk about excess pressure, delta P, P inside minus P atmospheric pressure, that is equal to 2T by R. So you can imagine a surface film means, suppose you have a glass plate like this, and below that another glass plate like this. In between two glass plates, there is a liquid layer. Here also you can take. There is a liquid layer between the two glass films. Suppose this is the liquid layer in between two glass films. So this liquid layer, suppose with respect to sides, it is like a curved surface, like this. Okay, if it is only one curved surface with the same radius, Then again delta P you can take P inside minus P naught, that is equal to 2T by R. So if it has two curvatures, two curved surfaces, one side one curvature, another side another curvature, then excess pressure you can write delta P is equal to, we can write like instead of 2T, T by R1 plus T by R2. T by R1 plus T by R2. That is T is T into 1 by R1 plus 1 by R2. Okay. So this is the way also you can take. So this is about certain applications regarding excess pressure. You can take a liquid drop, you can take soap bubble, you can take a air bubble inside a water, you can take between the two thin layers of glass plates, there is a small layer of liquid that is formed. For that also can calculate excess pressure like this. Suppose you can take a liquid drop in a water. I said just free surface of the water. Now inside a water at certain depth. In that case, how we can calculate pressure value? So this is the free surface of the liquid. Now at a H depth, there is a air bubble is formed. There is a air bubble here. There is a air bubble. Bubble radius is R, let us say. So here, what is the pressure inside this air bubble? Outside on the top of this atmospheric pressure P naught. What is the pressure inside this air bubble? That means we know excess pressure delta P, that is equal to P inside minus P naught normally. Okay, then I want to calculate first P inside. Suppose if it is just on the surface, P inside is equal to P naught plus 2T by R. Just above the surface, just below the surface here. But it is at a depth H, then what you need to calculate additionally? Means P inside the liquid drop, that means air bubble is equal to P atmospheric plus pressure due to vertical depth, that is rho GH. Are you clear this point? Where rho is the density of water. Okay, T is the surface tension of water. Then P inside at a depth H for an air bubble is equal to P naught plus rho GH plus 2T by R. Plus 2T by R. Are you clear this point? Okay. The pressure at a depth H is A is equal to inside pressure P naught plus rho GH plus 2T by R. Okay. So this is the way to calculate the pressure of a air bubble inside a water at a depth H. Okay. So this is about an application. So where we can see this liquid drops and air bubbles, all these means, suppose you can do a real-time application skating. Okay. In skating, the skater will do certain pads like this. Like this they will use. They will go on the ice. Okay. People used to do the skating on ice. No? Then in that case, what happened exactly? While doing skating for a person. That means there is ice blocks is there. This ice will continuously will contact with this skating plates. Okay. Then whenever it is going forward, first of all here, in between this skating plate and ice, ice will start whatever blocks of ice, that means solid, it will become liquid. So that at that time it will form because of the pressure. There is a pressure applying now because of the skating blades. Due to this pressure, the ice molecules convert into water, and that will form like liquid drops. It will form like liquid drops. The excess pressure inside the liquid, because of that, the drop will behave like a bearing, ball bearing. Okay. Are you clear this point? Because of this ball bearings of liquid drops, the skating will easily will go forward. So this is about an application to understood about how the skating phenomenon will be happen with respect to excess pressure phenomena. Okay. So this is one interesting and important application. So next, based on this, we'll go certain applications of related to soap bubble or related to liquid drops. What are the applications means? So how to calculate ratio of the masses? Ratio of the mass inside a soap bubble. Suppose we can take two soap bubbles. Soap bubble 1, soap bubble 2. Suppose outside atmosphere is there normally. Suppose you can imagine vacuum outside. Okay. Then what is the pressure inside? PI minus out vacuum pressure is 0 is equal to 2T by R. PI is equal to 2T by R. Actually, this application theoretically possible, but practically not possible. Why? Because outside is vacuum means 0 pressure inside 2T by R pressure. Immediately, this will blast. The bubble will be blasted. Are you clear this point? Okay. Yeah, but suppose if it is possible, then in that case, how to calculate the ratio of their masses? A simple way. Ratio of the mass of the soap bubbles. Suppose we have a relation PV is equal to nRT. Okay, where the pressure, volume, N is the number of moles, then PV is equal to mass by molecular mass, M by M into RT. Then M by M is directly proportional to pressure and volume. Suppose two are same volume, then M proportional to P. That is the inside pressure. Mass. Mass is directly proportional to pressure. Then from that you can write, if it is different volumes, you can take P1, V1. Then M1, M2, P2, V2. So in that case, you can take M1 by M2. That is equal to P1, V1 by P2, V2. What is this P1? Inside pressure of the soap bubble. What is that? 2T by R1. Into volume, 4/3 pi R1 cube. Similarly, this is P1, V1. P2, V2, 2T by, suppose same soap solution, then surface tension will be same. Then 2T by R2 into 4/3 pi R2 cube. Are you clear? Then P1, V1 by P2, V2 can calculate. 2T, 2T cancel. 4/3 pi, 4/3 pi cancel. R1 cube, R1 one time cancel, R1 square remaining. Here R2 square remaining. Then M1 by M2 is equal to R1 square by R2 square. R1 square by R2 square. That means the ratio of their masses is directly proportional to square of this radius of the soap bubbles. What I actually said outside volume is a vacuum, that is not possible. Then reality is outside is atmosphere you can take, then it is possible. Outside atmosphere you can take, then outside pressure at P0 you can take, atmospheric pressure. Then in that case, P1 is equal to what you can write? P0 plus 2T by R inside pressure. P2 is equal to P0 plus 2T by R. R1, 2T by R2. So in that case, ratio of masses, how it will be? M1 by M2 is equal to P0 plus 2T by R1 into volume V1. Similarly, P0 plus 2T by R2 into volume V2. Like this you can do. Are you clear this? Where V1 is equal to 4/3 pi R1 cube, V2 is equal to 4/3 pi R2 cube. This is about to calculate the ratio of the masses of soap bubbles in terms of atmospheric pressure and the radius of the soap bubble and the volume of the soap bubble. Okay. Next application you can see. Second application. Suppose the two soap bubbles of different size. So let us say soap bubble 1 this much size and soap bubble 2 small in size. Interconnect each other. Have you observed any time? Two soap bubbles are connected each other. 1 and 2. One is bigger, second is smaller. Then the radius is R1, this is R2. Then the question is that what is the radius of the interface? This is the interface is there, no? This is the interface. then they'll form a new bubble after certain time. Then what is the radius of the interface or radius of the new bubble that is formed? So in that case, how to calculate? By taking excess pressure again. Actually, pressure inside the bubble 1 is P1, inside the bubble 2 is P2. Normally I said excess pressure delta P is equal to 4T by R. That means if the radius is high, excess pressure is low. What does it mean? The drop is larger, the pressure is low. So that means now compared to 1 and 2, which has high pressure? Bubble 2 or bubble 1? Bubble 2 has larger pressure because radius is low, then pressure will be more. That means excess pressure now again between them you can take bubble 2 pressure minus bubble 1 pressure, P2 minus P1. Are you clear this point? When the two subbubbles are interconnected, at the interface, let us say the radius is, let us say R, then what is the interface radius? By using excess pressure, because the smaller bubble having high excess pressure. So P2 minus P1. Then what is P2 value? Where P2, P1 value again excess pressure you can take. P2 is equal to 4T by R2, P1 is equal to 4T by R1. Okay. So P2, P1 also can take excess pressures. Then total excess pressure delta P can write 4T by new radius R. 4T by R is equal to 4T by R2 minus 4T by R1. Because of same solution, then surface tension will be same. Then 4T common. Then you can write 1 by R is equal to 1 by R2 minus 1 by R1. 1 by R is equal to 1 by R2 minus 1 by R1. Okay. So from this you can calculate the radius of the interface of the two interconnected soap bubbles by using excess pressure phenomena. Are you clear this application? So these are the different applications based on the excess pressure calculations. So by this excess pressure value we understood, and based on the different applications we understood. Okay. So by this surface tension we can wind up, okay, with this excess pressure phenomena. Okay. So first let us recap this 2 minutes last. First we have calculated the excess pressure inside a liquid drop by using the concept of surface energy equal to work done by internal pressure, that is equal to delta P 2T by R, where internal pressure exactly if you want Pi minus outside pressure P naught. Pi minus P naught is equal to 2T by R. Then internal pressure is equal to Pi is equal to P naught plus 2T by R. Next we have calculated that application is used for soap bubble. Soap bubble we have two surfaces, inside surface, outside surfaces. So that we can write 2 times of 2T by R excess pressure, that is 4T by R, keep in mind, for soap bubble. Suppose air bubble you can take inside water, that it contains only inside surface, free surface, outside is connected with water, then again it is only one surface, then excess pressure is 2T by R. Okay. So that means you can take soap bubble and liquid drop, excess pressure will soap bubble will be more compared to liquid drop. Next, for a thin film that is formed between the two glass layers, suppose there is a curved surface that will of radius R, then excess pressure you can write again in that case 2T by R. Suppose if it is two curved surface it will form, then you can write T by R1 plus T by R2, that is T into 1 by R1 plus 1 by R2. Next, the air bubble if it is in a depth h from the free surface of liquid, then the inside pressure Pi is equal to P naught plus rho gh plus 2D by R. Rho gh is the static pressure, pressure due to depth. P naught is the atmospheric pressure. 2T by R is the bubble pressure. Okay. So like this you can take. Then skating application we discussed. Because of this pressure, liquid drops are soap bubbles that will make like ball bearings. Those liquid drops will behave like. Next, we calculate ratio of masses of the two soap bubbles in terms of their pressure and volume. 1 by m is equal to P naught plus 2T by R1 into volume V1 P naught plus 2T by R2 into volume V2. If two soap bubbles, if it is in contact with each other, then what is the common radius they will get? Interface radius. After combining together, you can write by using excess pressure difference from smaller bubble to bigger bubble. The delta P is equal to P2 minus P1. Where P1, P2 also you can take excess pressure values with respect to outside pressure. Then that is equal to 40 by R is equal to 40 by R2 minus 40 by R. From that 1 by R is equal to 1 by R2 minus 1 by R1. Provided that radius of the smaller bubble and bigger bubble if you know. Okay. So this is about the understanding about excess pressure and their applications. Are you clear one and all? Thank you. So I'll stop here. So Monday onwards I will start